Hello, we're from F-18 Hornet team and we're going to explain about the project of moving shockwave in two different cases. The roles of each member for this project is Alif and Kelvin in charge of programming, while Is and myself in charge of report documentation. The objective for this project is to study the flow properties of moving shockwave across the shock to enrich understanding and knowledge about moving shockwave at different cases, and also to build a MATLAB code to compute the flow properties of supersonic flow crossing a moving shockwave. The overall process for this project is divided into three parts, which is requirement, problem statement, and research and problem solving. The requirement for this project is we need to model two different cases of moving shockwave, which is direct calculation and also the iterative calculation. The problem statement is how to model two different cases of moving shockwave, how to build MATLAB code, how to evaluate the input parameter, how to create interface for a user. And lastly, research and problem solving. We discuss with teammates to model the cases, we do some research about the MATLAB code, and also did comparison with other team, do some manual calculation, and for the interface for a user, we're using GUI.
Hi, this is Is. For the theory, our idea is to convert moving shock into stationary shock by changing the reference frame. Then, we calculate the relative velocity by switching the direction of airflow and solve it as a stationary normal shock problem. Later on, we reconvert the reference frame to solve for gas velocities in the original reference frame. Moving on, the figure on the screen is showing our flowchart for MATLAB. First, we run the MATLAB program and key in the specific coding. Then we do trial and error to make sure the output parameters produced are correct with respect to given input parameters. If the output parameters obtained by MATLAB are not the same as manual calculation, then we have to redo and correct the coding until the output parameters are the same as what we have calculated manually. If the output parameters for trial and error is successful, then we can proceed with GUI.
Alif here. I will explain coding structure for non-shock velocity. For the non-shock velocity coding structure, I divided it into three sections. At section A, feature function is used to set the parameters as input. Section B is where theory of moving shock velocity is implemented. First, gamma and specific gas constant are set as constant. Second, we structure a code to calculate values of A1 and M1. Third, converting the gas frame to shock frame, I structure a code to calculate values of V1', M1', M2', P ratio, and T ratio. Fourth, with the P ratio and T ratio values, I structure a code to calculate values of T2 and P2. Fifth, A2 and V2' was calculated, here using the value of T2. Sixth, by converting back shock frame to gas frame, V2 and M2 values are calculated. At section C, feature set and string are used to set the parameters as output. Thus, by combining all the sections in order A, B, and C, the overall coding structure for non-shock velocity will look like this.
Greetings, after I'm talking and now I want to present the coding for the gauge calculation. So I split the structure to three parts. The understanding, this parameter is given and we have to find this parameter. The requirement that we have to use a iterative calculation. So we use, for the strategized part, we use a few equations to solve the calculation, but there's too much of unknown, so we have to guess one of the parameter, and the parameter we chose is the shock velocity. So to guess the parameter, we have to run the iteration with the loop equation, where the I is the number of loop. If the higher I, there's more complexity, but it costs more time. So to reduce the difference of the shock velocity between the loop, we have this equation, but for this equation, the initial shock velocity must be high enough. So when the difference of the calculator V2 and given V2 is less than 1, and break the loop as we get the shock velocity we want. So we design a GUI program to present it. For this part, it's combined with that if GUI to present it more efficiency and consistency. So for the solving part, I have a sample question with this condition and can check the answer with the Virginia Tech computer.
This is GUI flowchart. After run the GUI, two choice cases will be appear. Select one and insert the required input parameters. Data computation will be occur after the OK button is pressed. Output parameters will be displayed. End of GUI. Alif here. Graphical user interface GUI for both model cases are created. For our GUI, one main rule to use it is it only applicable for situation where the shockwave traveling into a region of stagnant air or air that itself moving same direction with the shock. Combining both model cases into one GUI, the left-hand side is non-shock velocity and right-hand side is unknown shock velocity. By clicking the non-shock velocity, the non-shock velocity calculator will come out and vice versa. The detail how to produce GUI can be referred from the first video project at Panet 2.45 until 4.12. I will show you how does non-shock velocity calculator works with two different problems. First problem is a shock wave propagates down a constant area duct into stagnant air. Second problem is a strong shock wave traveling into a region of air that itself moving same direction with the shock.
So here's the GUI program for our team, and we can show the unknown shock velocity here. And here we can set the input parameter. And calculate the output parameter. So this is a transmitter calculator and calculation actually.
Certain problems that we have encountered in doing this project is that during the coding process, the codes that we use were unable to produce the correct output values. Besides, more iteration is needed in order to obtain more accurate answers. Thus, the longer the time required for MATLAB to do computation.
Hi, Alif here. What things that can be improved? In terms of coding structure, we can improve the code to solve the problem where the shock wave traveling into a region of air that is itself moving opposite direction with the shock. In terms of GUI, back button to return to main interface can be created.
Objectives that we have achieved from this project are: first, we have studied the flow properties across moving shock. We also have better understanding in solving direct and iterative calculation for different cases. Last but not least, we are able to build MATLAB code to compute the flow properties of a supersonic flow crossing a moving normal shock. Alright, that's all from us, Team F-18 Hornet. Thank you.